Welcome. In this presentation, I will bring out the details, importance, how do we do, and its applications regarding information extraction and information retrieval. Okay. So in some sense, you have to keep your mindset in terms of understanding the differences, and commonalities between information extraction versus information retrieval. So we have a collection of documents, okay? But when you are given a collection of document, there are sentences there, okay? And sentences contain words, and a document contains many paragraphs, and there are many documents in a corpus. So first and foremost, what we want to do is we want to extract information from the documents. Okay, to understand the documents, we have to extract information. What do I mean by that? We are talking about the syntactic components of a sentence, the syntactic relations, which are basically grammar, structure of a sentence, and so on. Very mechanical approach to writing, expressing, talking, saying, speaking. But then we also want to extract, that is one part of that story. The other part is we also want to extract the context of the usage of words and the relevance, meaning, information hidden behind the words, hidden behind the relationships among the words. They are called semantics. So we want to extract that information also. And we combine these two things so that we can use and find similar, in a search pattern, we find such relationships and extract those information and also the semantics, the syntactic and semantics, and so that we can apply it for new documents, and bring those relevant documents in the search process. So that's why information extraction matters and how it connects to the information retrieval. So I will repeat this many times over the next few slides. Okay. So the purpose of information extraction is that it facilitates as the beginning, as the starting point of analysis of words, analysis of sentences. Okay, and so that it can be applied for various industries, various fields. When I say fields, I mean industries. Okay? The essential components of essential elements of information extraction is that there is a collection of documents. Okay, there is a collection of documents here, right? Essential elements are the collection of documents, diverse data sources, efficient extraction techniques, and meaningful output. So you use the extraction techniques against the collection of documents so that you get to some meaningful, useful, interpretable, analyzable outputs. So that is what is information extraction is. So information retrieval is coming as a second part. So we use that information extraction to apply, to bring the relevant document in a search process. So that is the difference. Okay. The importance of information extraction in NLP application is that I'm talking about information extraction. Okay, is that we can use data mining efforts on that extracted information, and we can do, for example, applications like sentiment analysis, and of course, the ultimate golden path is to retrieve, to predict and retrieve the right relevant document because somebody asked for some information, okay, in the search process. So, here is an example of saying, what is meant by semantic relationship via, in our case, association metrics, called cosine relationships, cosine correlations, okay? Cosine association correlation matrix. So if somebody is searching hotel hotel on a beach, let's say I'm in Germany, I live in Germany and the system knows it. Google knows everything, okay? System, I type hotel, on a beach, and there are the associated collection of document knowledge base is that the hotel is on a beach, the hotel is in Germany, the hotel gets 5 stars, a particular hotel, okay? So the concept matching is that the hotel is matched hotel, but then the relationship matching says that the hotel should be on an ocean beach, okay? And it has to have 5 stars and it should be located in Germany. All these things are connected matching relationships. The attribute matching is beach and beach, okay? It's an attribute that the hotel should, be on the beach is an attribute of the hotel. So what we are saying is that in the system-wise, in the analytical space, we are looking at, technically speaking, the moment you say hotel on a beach in a search engine, and let's say you also do, it can figure out based on Google knows we are in Germany, okay? So, but it's okay. The second query is the hotel in Germany, okay? Then what we are really saying is that this is the document. The query 1 is this, that connects beach and hotel. Query 1 is hotel on a beach, right? It connects hotel and beach. So document is here, okay? Document vector space. In the hotel beach, assuming only 2-dimensional hotel and beach, okay? If there are many words in that sentence, then we will have multi-dimensional space. But for illustration purposes, we are only talking about 2-dimensional space here. So in the 2-dimensional space, hotel versus beach, the document is here. The query 1 will be closer to document 1. That's what it says, right? It's closer. It's not going to be closer. Query 1 is not going to be as close as query 2 to document 2, D2. Query 1 will be closer to document 1. Query 2 will be closer to document 2. So it will extract D1 and D2. But in the collection of documents, the hotel, because it knows, the system knows that I have been, system knows me, Google knows me, it will also get only relevant information because of historical connection. You'll see temporal, knowledge network, knowledge graph. So it knows that deeply in the knowledge network, I only use 4-star or 5-star, let's say only 5-star, okay? So that it's simplified in this case. Then it's going to bring out these 3 documents from the knowledge base, from the collection of documents that the system has. That's called knowledge base. Okay, so this is how it is. So the Q1 is more associated with D1, Q2 is more associated with D2. The association is measured by cosine similarity, cosine metrics, cosine association, cosine correlation. So this is what is called the semantic retrieval. Okay, it goes into the correlation at the vector database level of the keywords, which are estimated based on many thousands of documents, which words are closer to which word. Okay, that's basically it. And the closeness is measured by cosine similarities. So in the information extraction, we are going to go through all these concepts. I kind of already talked to you about information extraction and its purpose, its importance in NLP applications. We will also talk about named entity recognition. What are the basics of that, types, and what is meant by entity extraction. I'm very specifically talking about entity, not information extraction. Okay, entity extraction versus named entity recognition. So we recognize an entity, and then we extract, information related to that entity. That is entity extraction. And then the relationship extraction, identifying entity relationships among them. Okay, we want to do that also. That's how we can build the graph network. And what are the steps in entity and relation extraction? Rule-based versus mission-based. Quickly, we'll go through that. Dependency, what does dependency parsing means? For relation extraction, grammar-based feature extraction, and open information extraction. Okay. So so let's quickly go over this slide where I have three web text here, simplified, just a web text can mean, thousands of sentences if needed, right? But we are only talking about one sentence here, basically, each of them three texts, right? The second sign of the zodiac is Taurus. So in that sentence, the moment I read, the moment even the system reads it, there is an implication that there is something called first sign, there is something called third sign, and also what is maybe a total collection of signs in the zodiac system. So it will go to the co-referenced documents in the database and extract the list, because it's already talking about 1, 2, 3, 4, 5, and also we want to know the whole collection. So it's going to extract the full collection of zodiac signs and its names and where they are ranking and in which Taurus should be the second one. That's what you see the output as the structured sequence output as a list here. So that is the extracted structured sequence list information based on the text, the second sign of the zodiac is Taurus. Likewise, when the system reads strokes are the third most common cause of death in America today, there is already an implied collection of common cause of death in America, and in that list, the ranked list, third one should be stroke. How does it get that list? Co-reference documents and collects all those things because of the implied information there. That's what the semantics is about, and it will bring out that list. First is heart, second is cancer, third is stroke, and so on. Likewise, the third one. Okay. So in picture, what I'm trying to say is that given a corpus, and the corpus reads, the system reads the corpus details, then it is bringing all the documents that are relevant to that, co-reference documents, and then put together, extract text summarization and summary including key points. These are all part of the information extraction. Okay, there are many of them, and this is one of the summary key points. And also it will extract the syntactic and sentence level grammatical relations like subject, predicate, object, and modifiers and so on. They are called triples. Okay, and they're all to put together and enriching the entity. In this case, the entity could be, for example, Netra Sambamurthy, and Netra Sambamurthy got his PhD from University of Pittsburgh, 1988. Netra Sambamurthy is studying. That's a separate document, right? He's a adjunct professor at Northwestern, also at University of Texas in Texas. He's doing consulting for the last 25 years, and all coming from different documents. Okay, so now we have an entity. That entity, Netra Samurthy, is enriched, and there is a graph representation. Relationship among various entities, edges, nodes, and then nodes and edges, and then their relationship. At what depth? It can go up to different depth levels if it needed. If you want to extract extract and provide the relevant information to the searcher. Okay, so this is how the network is constructed. There are 8 types of information extraction. We saw there, text summarization. That's one of them. Okay, and tokenization is another type of information extraction. N-grams is another one. Named entity recognition. We are going to see that. Parts of speech, we already kind of saw the example speaking about me, Netra Sambamurthy. Parts of speech tagging, sentiment analysis you can do. These are all different types of information extraction. Some are very sophisticated, some are very simple. Tokenization is much simpler than text summarization and sentiment analysis. And then of course, if we want to also know the dependency graph, without dependency graphs, knowledge graphs especially, dependency graph versus knowledge graph, we are going to talk about that, but knowledge graph, without that we cannot go very deep level of entity relationships. Okay, so we need that. And topic modeling, aspect modeling. Aspect modeling means basically techniques for identifying many features of a text and put them together to identify and predict certain other things. For example, in the healthcare example, medical research, patient surveys, electronic health records, coming together can extract common themes about feedbacks from the feedbacks and medical records, and it can identify side effects, who is getting what type of side effects under what conditions for a specific type of drug, and what are the patient concerns. That's called aspect modeling. So all these things are information extraction. Okay, there are different types of information extraction. So what is the difference between dependency graph and knowledge graph? Dependency graph is all about one sentence, relationships among components in a one sentence, or elements in a one sentence, or the subject, predicate, object, or the entity in one sentence. But knowledge graph means collection of sentences, collection of documents, and so it will be a graph network of subject, entities, and various relationships among entities. The entity supporting items, like for example, dog is chasing a ball. The entity is dog and ball, but then dog can also get connected to dog is playing with a boy, or a runner is running with a dog. A runner is running with two dogs, for example. So these things are the various deep, expanded network of words that are getting connected. They are called the knowledge graph among the words, among the entities. And here is an example. Elon Musk founded Tesla is one sentence. There is a relationship there. That's called the founding. Okay, action is founding. So Elon Musk is CEO of Tesla. There is a relationship between Elon Musk and Tesla, and the relationship is, he is the CEO. Tesla was founded in year 2003. That's the relationship there. Tesla and the year, temporal component there, year 2003. That is the year of founding. But together, there is a lot more enriched information, right? Enriched information. So that is called knowledge graph. So knowledge graph is what is represented in the right side here. And here also it's there. Okay, so this is called the knowledge graph. Knowledge graphs are very useful for semantic search, recommendation systems, and data integration, and are commonly built using softwares like Neo4j, RDF, GraphDB, and each of them have their own query language. Okay, it's all well laid out, well constructed, well developed. My point is, this is the difference: dependency graph versus knowledge graph. Okay, and in summary, dependency graph is all about one sentence, single sentence. It's about the grammatical structure. Okay, it's talking about the words, tokens. It's talking about subject, object, modifier. It's talking about essential NLP tasks like parsing, sentiment analysis, relation extraction, and so on among the words. But in the case of knowledge graph, we are talking about real world knowledge in structured format. So even though it is a graph network, it's a structured format. It will be handled by the system. Okay, the Neo4j does that. It's an open source software for that. And it works at document level, database level, or even at global level. And it's talking about the entities, not just the words. And it's talking about the entities, not just the words, which is the dependency graph. And it is talking about semantic relationships. Who is the parent company? When was it acquisitioned? And who is the CEO and so on, for example. Right? In this case, Elon Musk founded Tesla. The knowledge graph is this. Okay. But here, it's only as a dependency tree. It's called a dependency tree. This is called a graph because it goes deeply into many levels based on multiple sentences and multiple documents. So, what is the NLP task in dependency graph or parsing, sentiment analysis, relation extraction? It becomes a question and answer because it's more sophisticated. It can provide that sophisticated responses, and that's why it's an AI task. It's a question answering, search engine, recommendation systems, and so on. So you can see how simple NLP processing versus AI tasks differ. Also, often we don't talk about those things, but it's not just the NLP alone. Is you have to go deeper than that in order to do AI with the NLP. There are many models of information extraction. So you know what is meant by information extraction, okay? And there are many models. In the case of large language model, there is something called zero shot versus few shot, also called K shot. It could be 2 shot, 3 shot, 4 shot, 5 shot, 10 shots also. Here short means examples. You don't give any examples to ChatGPT, just ask the question, that's called zero shot. But if you give examples, 4 to 5 examples, because each of them will enrich a deeper level of the request that you are planning to do, then it becomes K shot or few shot in LLMs. There is also distance supervision for relation extraction. There is some overlapping terminologies here. For example, basically it says, bring together some distant databases into the new new database, and then mix them, mingle them, and then use them for application development. So and use that further to do the relationship extraction. That way knowledge network can be very dense as well as very rich. So we will have NLP models for entity and entity relationship extraction. Also, we can use what is called BERT-based models, transformer-based models. The difference between them is that BERT is just weights and biases based on training model, training huge collection of data. That is so basically Google gave away the weights and biases. But transformer model goes one step ahead. It also trains. Besides, it trains. Based on new collection of data to have its own weights and biases. Both are context sensitive. Okay. Graph neural networks for IE. So when you have graphs, then you can build predictive models on that. That's where the graph neural networks come in place. And large language models also can be used in information extraction. We talked about in the last slide. We need to use co-reference resolution techniques so that we can enrich for your area of application, for your set of documents, for your company, so that it's the intellectual property stays within your company, right? You need co-reference solution. That's where the RAG models come in. Okay, we'll talk about that in week 8. And also, we need to be not just finding information extraction for for just a cross section of data, cross section of documents, but also sometimes documents might be connected over time. So we have to bring out the temporal information extraction as part of handling time expressions. Okay, so we do that. We have methods to do that, to normalize the data over time, and so that it all makes sense. The current level of ChatGPT is amazing. It does a wonderful job of all those things. So in the end, we will talk about a couple of examples in both in healthcare, and a couple of examples, one from healthcare, one from finance. So what is meant by named entity recognition? It's a subtask of information extraction that identifies, classifies, and extracts named entities from text. Named entities are common entities like persons, organizations, locations, dates, numerical values within text. These are all called named entities. Named entities aid in data annotation and improves information retrieval by categorizing important textual elements together. These are the people, these are the building, these are the places, these are the things, these are the events, these are the events. These are the books, these are the authors. So once we have that, the keywords, enriched information, that's what the entity recognition is about. Okay, and when we build the relations, the dependency graphs, becoming knowledge graph, it's very powerful for information extraction as well as for other predictive applications. Let us define entity extraction versus named entity recognition. The broader definition of entity extraction means we get substantial data element beyond merely named entities. For example, In this right side notes, John Doe was diagnosed with type 2 diabetes in 2015. He was initially prescribed metformin, but after 6 months, his dosage was increased to 1000 mg per day due to poor glycemic index, glycemic control. So if you do just entity named entity recognition, you will just be providing some the entity information such as name of the patient is John Doe, the disease he has is type 2 diabetes, year of onset is 2015, diagnosed in 2015, initial and the prescription drug is metformin 500 mg per day. Okay. But that is just a named entity recognition. But then the fact that after 6 months his dosage was increased. After 6 months his dosage was increased is a lot more valuable additional information, because that means it was not under control with 500 mg per day. This is called substantial data element beyond merely identifying the named entities. Such substantial data element are basically giving more enriched information about the entities, and it is very important to collect that also. So entity extraction refers to such activities. So unlike a named entity recognition, entity extraction captures diverse information types, broadening the scope of analysis opportunities. For example, the analysis here might say that his initial treatment was out of control, which is a very important conclusion. So the applications beyond named entities requires this kind of substantial data element that enriches the text data. Okay, and it facilitates comprehensive understanding across various contexts. Okay. On top of it, we also want to do the relation extraction, identifying entity relationships. We are leading slowly and steadily towards what is called the knowledge graph. Okay, that's where the knowledge graph with semantics is the best information that you can get from a collection of documents, and that's your ultimate goal. So identifying entity relationships, relation extraction identifies and categorizes the relationships between entities within unstructured text data effectively. Okay, that's what relation extraction means. And the common methods employed are rule-based versus machine learning, which means supervised learning, deep learning, and so on. The application of relation extraction is critical in knowledge graph formation, information retrieval, as well as semantic search advancements, because once you have the advanced extracted knowledge graph which has the substantial data elements about the entities, then we have very powerful search mechanism, information retrieval applications, and also knowledge graph applications. So how do we do the entity and relation extraction? Basically, you have to do the pre-processing, always clean the data, organize the data, manage the data, and then start doing the extraction work and identify the entities as well as the substantial data elements there, and do the relationship mapping as a network, so that the interdependence about the nodes and edges are clearly laid out and usable. As I said, there are rule-based, and that's what we started initially, but then machine learning techniques, it is very simple, and it is oftentimes very precise because humans are involved, but machine learning techniques employ statistical models trained on labeled data, enhancing adaptability and accuracy while requiring extensive data sets, and that is okay. Data is very valuable, and more and more data are collected by both machines and by humans. And rule-based methods excel in deterministic scenarios, while machine learning offers scalability and learning capabilities, continuous learning capabilities. So those are the methods we use. And as I said, dependency parsing is very important. We talked about, for example, Alice loves Bob. Alice is subject, loves is the predicate, and Bob is the object. And it clarifies dynamic relationship between Alice and Bob. Um, those things are possible because of the information relationship extraction. And grammar-based feature extraction is also important. We are not throwing away grammar-based feature extraction, which are syntactic, but we use that to enhance all our subsequent work. Use that to enhance the semantic relationships, combine them so that the prediction becomes a lot more enhanced. So there is in the LLM model there is something called zero shot and few shot information extraction. Zero shot means not giving any examples, just ask the question and it answers you. But sometimes you can give examples to the LLM and it will take out the vectors or the tokens and combine it to the existing vector database and then enrich your response. Okay. So few shot also means k shot. K could be 1, 2, 3, 4 number of examples you give, so that your extraction becomes very relevant for you. State of the art LLMs demonstrate significant capabilities in zero shot and few shot learning for diverse extraction applications. Distance supervision refers to utilizes existing databases to generate label data for training relation extraction models, and it enhances the scalability and reduces labeling costs because of the existing databases about the labels and documents and entities and so on, enabling efficient extraction from vast data sets. There is still some problems in terms of noisy labels. Reliance on imperfect labels can lead to inconsistencies, potentially degrading model performance during extraction tasks. So it's good to use, but be models. So eventually you are building graph neural networks, okay? Because you have the graph and then you can build neural networks so that you can predict for future documents or additional documents or new documents. So that is the idea here. So graph neural networks, basically are designed to model relational data through neural network architectures. Effectively, the relational data are about the entities and which are the nodes and edges. We enhance the relational analysis, using complex, capturing complex relationships and data, improving the accuracy and depth. We use graph neural networks and it fosters advancements in applications such as knowledge graphs, social networks, and semantic search again. Okay. So that's the ultimate thing anyway, okay? Remember that, so knowledge graphs are the ultimate things, which are enhanced by the information extraction. The large language models in information extractions are extremely powerful in semantic understanding, enabling nuanced, context-aware information extraction across diverse data. These models leverage extensive training data, and BERT is one of them, and also transformers, which you can use as a methodology to train with your own data. So core reference resolution techniques are, I already mentioned that's how you increase the value of the weights and biases, which are already hard to compute and hard to calculate. It takes millions of dollars, and BERT is one of them. And how do we enhance that? That's where the core reference resolution techniques come in. RAG models are one of them. We are going to talk about it in week 8. So basically RAG models brings in new vectors, new vector database from the current documents, which may or may not be there in the LLM, BERT LLM. So, and then these two databases, BERT vector database is combined with the newly created vector database from your owned your organizational data, and with these new combined vector databases you can predict better for your own applications. That's the idea. So temporal, we also need to take care of the temporal information extraction, because for example in the healthcare example I talked about, John Doe was diagnosed with the type 2 diabetes in 2005, and then he was he was administered with metformin for 6 months. 6 months is important, 2005 is important, and then after 6 months he was given, because it was not out of control, it was still not controlled. Diabetes 2 was not under control, glycemic there is no glycemic control. So there is a new prescription that increased the dosages to 1000 mg per day, and those time points are very, very important, and those kinds of temporal information extraction is also important, and it helps manage and predict better with your documents. And there is some normalization you have to do in terms of dates and durations, and the new types of measurements like months and years, weeks, and so on. All those things, once you normalize it, once you uniformly you define it across the document, then it becomes applicable very effectively using temporal information also. Okay. We talked about this, healthcare as an example. So, extracting relationships between specific drugs and diseases significantly advances personalized medicine research and treatment approaches, and enhanced extraction techniques facilitate discovery of novel drug interactions, driving innovations in therapeutic strategies. So, supporting the clinical decision support system. Okay. Similarly, we have examples in the finance also. We can talk about it. So, the main point here is that there are information, you have to extract the information, and I defined what are meant by information bits, information, and then we enhance it with enriched information which are applicable at the semantic level, and then we not only, we also defined about NER, that is named entity recognition, but again, named entity recognitions are supported with the substantial data, additions to that, so that it becomes, semantically applicable named entity recognition, named entities as a network, as a graph network, and that's our ultimate goal, and it has very powerful predictive applications for new documents or for the existing documents. Thank you very much.